Greetings, this video is for the clinic project Brain-Computer Interface Controlling the IoT. IoT refers to the interconnection of computing devices embedded in everyday objects via the internet, enabling them to send and receive data. The issue at hand was individuals that suffer from paralysis that due to their condition have difficulty completing simple tasks like turning on a lamp or cooking food. Because of this, we created an interface that even people that can't use their limbs are able to control, using only their eye movement. For this project, we used an emotive EEG headset. EEG refers to using small electrodes attached to the scalp to record the electrical activity of the user's brain. Each electrode monitors a region of neurons, or node. This is an electrode map of the headset the emotive software provided us with. The electrodes we were interested in were O1 and O2. The O stands for occipital lobe, the brain region in question. This is because we used VSSEP, visual steady-state evoked potential, a phenomenon that occurs in the occipital lobe. When the user focuses on a flashing light source, the frequency at which the light flashes is mirrored in the occipital lobe. Here's an example of that in video. So by measuring the brain activity in the region and performing a Fourier transform on the signal data, we are able to determine the frequency of the light source the user was looking at. This is an example of the initial graphing we did. The user was staring at an 11 Hz light source, which was the frequency we obtained. Building on this principle, we created a web page with 4 flickering lights at different frequencies, the controls, that allow the user to maneuver through the icons representing rooms and devices within these rooms. The user is able to control these devices and toggle them on and off. Here's a video demonstration. Our algorithm determines if the user is looking at the button by 3 criteria. If the peak frequency occurred at the same frequency for 5 seconds straight, if the peak frequency had a magnitude at least 4 times the average of the other frequencies for 5 seconds straight, and if it occurred at one of the 4 frequencies of the buttons. Once a peak is detected, the website index is updated and a signal is sent out to an IoT device if necessary. An index was used to simultaneously change the website on all devices so users can switch on the fly on any device that has access to internet and a browser. This basic website can be expanded to control any number of devices. So here we will soon see the light turn on because the user is looking at the select button. The user was looking before at the left button, so it switched to a different device or different lamp. So in a bit the user will turn on the device just by looking at the select button. There we go. We concluded that our goal was definitely feasible, but wasn't consistent enough for practical use. For the future, ideally, we would have access to a more accurate headset, as it did have some inconsistencies on a day-to-day basis. And we would also like to conduct tests on more subjects to get feedback for actual usability instead of just functionality. I hope this video was informative. We would like to thank Dr. Polakar for his continued support throughout the semester.